In this section, we're going to look at solving equations that happen to involve trigonometric functions. So when I look at something like the sine of theta equals 0.45, I can think of this in a couple of ways. One way would be to look at a graph of the sine function. Okay, so if I say I want to know for what angle theta the sine is equal to 0.45, I can also think of that as saying on this graph here, for what x values will the y value be 0.45? So, 0.45 is, right about there, I suppose. And so if I kind of just draw a horizontal line, I'm asking, when will the graph of the sine function have y values at 0.45? And you can see that there's lots of answers to that question, right? We'll go ahead and stop there. So there's lots of answers to that question because there are in fact many x values on that curve that where the y value is 0.45. And we can also think of this as asking us on the unit circle, where will the y value be 0.45? Remember, the sine function gives us the y value of a terminal point on the unit circle. So I could also go to y equals 0.45 here on the unit circle and say, okay, when's this going to happen? So clearly right about there and right about there. But we also understand that we can go around the unit circle as many times as we would like to. So really, it's not just these 2 points, but it's this point plus 1 revolution around the circle, plus 2 revolutions around the circle, and so on. Every time I land on this point, that would be a valid angle that would give me the sine of theta equals 0.45. All right, so with this knowledge that we should have lots of solutions, let's go ahead and take a look at, okay, how do we get at least one of them? So I have the sine of theta equals 0.45, and I notice that 0.45 is not one of my special values. Okay, so it'd be one thing if I was asking for when does the sine of theta equal 1/2 or something like that, but 0.45 certainly isn't a special value. So at that point, we're going to allow technology to help us a little bit. So we understand that if the sine of theta equals 0.45, I know that then theta would equal the inverse sine of 0.45, because the inverse sine function kind of undoes the sine function. And one way some people also like to envision what's happening here to get from this point to this point would be to say, I'm going to take the inverse sine of both sides, so the inverse sine of sine theta and the inverse sine of 0.45, and then of course the inverse sine and the sine essentially zap each other, and you're just left with theta on the left side. So if you want to think of it that way, that's just fine. I'm also okay with you just jumping straight from this line down to this line. Okay. But what we can do is we can type that in our calculator, and our calculator will tell us that that is approximately 0.467. Now let's go to the graph here and make sure that that seems reasonable. So 0.467, it looks like my first solution should be right about here. And let's remember that pi over 2 is about 1.57. So this is a little under a third of the way to pi over 2. So I'm feeling pretty good about the fact that I got 0.467 here as a solution. That seems to agree with my graph. And let's also see if it kind of agrees with our picture on the unit circle as well. So we're claiming that this is an angle of 0.467, and I guess I should note that, of course, this is in radians at this point. have my calculator in radian mode. So let's see, does that make sense? 0.467? Well, sure, this looks like it's about a third of the way to pi over 2, which is approximately 1.57. So I'm feeling pretty good about this answer. Okay, but then the issue is we can see from the graph and we can see from the unit circle that that's not the only answer. All right, so what I suggest first is let's remember that the sine inverse is always going to spit out values that are between negative pi over 2 and pi over 2. This is, so in other words, when you type the sine inverse of any value between negative 1 and 1, it's always going to assume you're asking for an angle in this region. And so this value over here, I can see, is not going to be given when I use the sine inverse. But we can see it right there. It exists, right? That should be a solution. So let's think about, okay, how does this angle over here compare to my 0.467 angle that I already got? Well, it seems like what's happening here is that over on this side, that this angle sure visually seems to be the same as my 0.467, but it's just measured from the negative side of the x-axis instead of the positive. And in fact, that's exactly what's going on. So since this negative part of the x-axis, or in other words, this value right here, is at negative pi, or sorry, excuse me, not negative pi, at pi, then what we can say is that this angle that I drew here is found by taking pi, so rotating all the way around, minus the 0.467 that I already found. Okay, so this angle is pi minus 0.467. So we can say also theta is approximately pi minus 0.467, which is approximately 2.675. All right. And let's just make sure that coincides with what's going on over here. It certainly seems like the distance from here to here, 0.467, is the same as the distance from pi back to this other solution. And that certainly looks like it's right about at 2.675. After all, pi is 3.14. So it seems to agree with our unit circle here and the graph of our function. But we have one other order of business. So we've got two solutions, one of which the sine inverse spits out at us, the other of which we had to use our knowledge of the unit circle to figure out. But then the other issue is that those aren't it either. There are more. Okay, so looking at the graph here, I know that if I take this value here and I add 2 pi to it, let me go back to my old color here. So I take this value and I add 2 pi, then I'm going to land on another solution. Okay, and that's going to put me there. And then if I take the second solution there that I have right here and I add 2 pi to it, that's going to give me another solution. And the same goes for subtracting 2 pi. If I take that original solution that I found and instead go back the other way, back to here, subtract 2 pi, then that's going to give me another solution. So, and then of course looking at the unit circle, if I add 2 pi to any angle or I subtract 2 pi from any angle, I'm just going to end up in the same spot on the circle. So in fact, here's what our solutions really look like. I'm going to put this in a different color just to distinguish this is our final answer. What we would say here is that theta can be approximately 0.467 plus 2k pi, meaning I can add any multiple of 2 pi that I want, or theta is approximately 2.675 plus 2k pi. And then I just add here where k is an integer. And remember, an integer is just any sign number, right? So -2, -1, 0, 1, 2, and so on. So here's the full solution to my original equation. The sine of theta equals 0.45. It's approximate because I had to use my calculator to give me an approximation. And then also just note that this is the full solution here, and so you may be asked to give the first 4 positive solutions, for example. Okay, and so instead of expressing it this way, you would use this formula to find some of the other solutions, but this encompasses all infinitely many of the solutions that we know we have. And then down below here, I just made a note that if you already have a solution to the sine of theta equals a, then a second solution is always found by taking pi minus that first solution. And we saw that happening right here. So let's now take a look at an equation that involves the cosine function. So we're looking at the cosine of t equals -1/2. So like we did in the last problem, let's find -1/2 on the graph of cosine. So we can see we should have a solution here and a solution here, and one right here, and one right here. And we also need to realize that when we're looking at the unit circle, that the cosine is the x value on the unit circle. So when I'm looking for -1/2 here, I'm going to look on the x-axis, so that puts me there. So that gives us a solution here and a solution down here. Okay. Now I typically find it easiest to think about things on the unit circle as opposed to the graph of cosine, but you may like the graph better. It really doesn't matter. But what I hope we recognize, regardless of kind of which of these pictures we visualize, is that when we see cosine equals -1/2, that is a special value. That's one that we should know without having to pull out our calculator and use the inverse cosine. All right, so as I look at this picture here, I can see that the angle we're talking about here is this one. And so when the cosine is equal to -1/2, from our knowledge of the unit circle, we should be able to pretty quickly say, I know that t equals 2 pi over 3 is the angle that will give me -1/2 when I take the cosine. Okay, so that's this value here, 2 pi over 3. That's this angle here. All right, and we can go over here, 2 pi over 3, there's pi over 2, there's pi, so 2 pi over 3, it certainly seems reasonable, is right about there. All right, so that's one solution, but again, we can see there's another one. Okay, we can see there's another one. And I guess I should just take a pause for a second. Remember that if I was to use the inverse cosine, remember the inverse cosine always spits out values between 0 and pi, so the upper half of the unit circle, and so this would be the value that would get spit out if we took the cosine inverse of -1/2. Okay. All right, but let's take a look at this other one. So here's my other solution that's visible on the unit circle. And so I need to go all the way around to here. But if we look at the symmetry of this situation, it would certainly seem that if I just took this angle, the 2 pi over 3 angle, but I took it in the clockwise direction instead of the counterclockwise direction, it certainly seems like I would get to this red solution here. And in fact, that's exactly what happens. So if I take 2 pi, that would be going once around the circle, and then I backtrack an angle of 2 pi over 3, I should end up right here. So we can say 2 pi minus 2 pi over 3 is another solution. And of course, I would like to put this together, so common denominator would suggest I say 6 pi over 3 minus 2 pi over 3 is equal to 4 pi over 3. Okay, and you may have just looked at exactly where this was on the unit circle and also known that it was at 4 pi over 3. All right, so we have these two solutions here. Let's see, 4 pi over 3, that seems reasonable. 4 pi over 3 is less than 3 pi over 2, so there it is on our solution, or excuse me, on the graph, is that second solution. All right, but also we look and we see that if we add copies of 2 pi or subtract copies of 2 pi to either of these, we just end up in the same spot again. So just like in the last problem, our full solution would be to say that t is equal to 2 pi over 3 plus 2k pi, or t could equal 4 pi over 3 plus copies of 2 pi. And then just to make this official, we would say where k is an integer. So there's our solution. Now there's a caveat here that I do want us to talk about a bit, and that is if you look down at the bottom here, here's what I did. Once I had one solution, I took 2 pi minus that one solution, and that gave me the other one on the unit circle. But notice it says, or what you could do is say that the second solution is just the negative of your first solution. Okay, so let's see why that's true. You remember I said that this angle, if I just went back in this direction clockwise, it would put me here. Well, certainly it's valid to say go around 2 pi and then backtrack that much, but I also could have just said, let's just go the negative of that angle. Okay, so let's just make a note here that if instead we had decided to, instead of saying 4 pi over 3 plus 2k pi is my other solution, we could have also said negative 2 pi over 3 was the other solution. And in fact, if you take negative 2 pi over 3 and you add 2 pi, and of course that would be negative 2 pi over 3 plus 6 pi over 3, you of course get our answer of 4 pi over 3. So if you want to use this principle that the second angle is just the negative of the first, that's completely fine because the solution remains the same, because clearly 4 pi over 3 and negative 2 pi over 3 are both included in this, right? To get from 4 pi over 3 back to negative 2 pi over 3, I just put a negative 1 for my k. So it really doesn't matter how you do that, and you can think of that in whatever way is convenient for you. Lastly, I'd like to look at an equation that involves the tangent function. So first, let's go ahead and get a sketch of this. So we remember that there are vertical asymptotes at pi over 2 plus copies of pi and minus copies of pi. And remember, that's because at these points, the cosine is 0. And tangent is sine over cosine, and we can't divide by 0. And then in between these asymptotes, we're going to have this type of action in each of those intervals. So we can get a quick sketch here. Now in this problem we have 2 times the tangent of x is equal to 8. So I think probably a good starting point here would be to solve for tangent first. In other words, get it by itself. After all, the sine and cosine were by themselves in the previous 2 problems we did. So we have the tangent of x equals 4. Now 4 shouldn't necessarily ring a bell as a special value, so we're going to go ahead and just use the inverse tangent and get an approximate answer here. So we would say x must equal the inverse tangent of 4, and that's approximately equal to 1.32. So let's see if that's pretty reasonable. Okay, so here let's say 4 is right here. Okay, I know I didn't label my y-axis, but just kind of bear with me and my sloppy graphing here. And sorry, this is not a horizontal line at all, is it? Okay, forgive me for that. But here we go. So here's a solution, and it certainly looks like that puts us right about here. Remember that pi over 2 is about 1.57. So does it seem reasonable that 1.32 is right here? Yeah, I think that seems reasonable. Okay, but now we need other solutions. We need one right there. We need one right here. One back here. So how do we get to these, right? With sine and cosine, we kind of had to think that through a little bit. With sine, remember we got another one by saying pi minus the first solution. With cosine, it was 2 pi minus the first solution, or the negative of the first solution. But let's take a look here. Remember that the tangent has a period not of 2 pi, but of pi, right? Tangent has a period of pi. And also notice that every interval here between vertical asymptotes has exactly one solution. And it looks like it's happening, kind of at that, it's certainly happening at the same sort of behavior point of the function. And so what we can say here is we actually don't have to search for another solution. We have all infinitely many of them for free. Because I can see that from here to here is just plus pi. And I can see from here back to here is simply minus pi. And so my full solution here would be to say x is approximately 1.32, but if I add copies of pi, I get all the other solutions, as long as I'm talking about k being an integer. So I'll just designate that, where k is an integer. So when you're solving a problem that involves tangent, you actually kind of let off the hook just a little bit. It's a little easier. So you just need to find a solution, and then if you just tack on copies of pi, then you've got all the rest of them without any more work.